Hello everyone. In this video we're going to be talking about the inverse of a linear transformation. So let's get right into it. So suppose I have a linear transformation, let f from Rn to Rn. So it's going from Rn to the same space Rn, be a linear transformation or a linear map. And let's suppose that this transformation is one-to-one and onto. So it is injective and surjective. Then we know that such a function has to have an inverse. Just remember that, well, if I have a map like this, what this means is that I have dots like this, and then there is some elements in this set here. One-to-one, it just means that every element goes to different elements. So this goes here, maybe this goes here, and this goes here. And onto means that everything in here is coming from something in here. In that case, I can, if this is my map F, let me just write F here, I can come up with an inverse map by just tracing back where points came from. So I know that this point came from this one, this point came from this one, and that point came from that one. And this is going to be what we call F inverse. But if you have a function that is one-to-one and onto, then there is an inverse function. And the question is if, so we do have some inverse function from Rn to Rn. And the question here is the following. If f itself was linear, is the inverse linear? Is f inverse also a linear map? And the answer is going to be yes. So let's prove that. So if f is linear, remember that that means two things, that f of u plus v is equal to f of u plus f of v, and two, that f of lambda u is lambda times f of u, and this is for all u and v in Rn, and for all lambda in the real numbers. So let's see that f minus 1, so f inverse, is linear by proving the same two identities. So we have to check 1 and 2, but for f inverse. So let's see what this means. Suppose I do f inverse of a sum of elements. Then what does that mean? Well, because it is onto, because the map is onto, I know that u has to come from somewhere. So let's say u has to be an image, u has to be in the range. So u is f of a, and v is also in the image, so it has to come from somewhere, call it f of b. Then I can substitute those, that is f of a, u is f of a, and v is f of b. Now, f itself is linear, so I can use linearity on these two elements to write this as f inverse f of a plus b. And here I am using that f itself is linear. Okay? And now I know that f inverse is the inverse of f. So f inverse of f inverse composed with f, is whatever I had there. So the answer to that is just a plus b. And well, but that's not exactly what I want. I want the answer to be f inverse of u plus f inverse of v for it to be linear. But a itself is f inverse of u. And here also, if u is equal to f of a, then a is f inverse of u, and b is f inverse of v. So I can substitute for a, call this f inverse of u, and B is F inverse of V, and that is precisely the property of linearity, that the map applied to a sum is the sum of the map applied to each element. All right, let's see what happens with the second property. So for the second property, I have to see what happens to F inverse applied to the scalar of a vector. And I'm going to do again what I did before, which is substitute U by an image. So U is in the image, so U is F of A for some A, and then use linearity of F to bring that lambda inside this F. And now F inverse composed with F is itself the element lambda A, and A is lambda times F minus 1 of U. Therefore, F inverse applies to a scalar of a vector is the scalar times F inverse applies to the vector. So this means that the map F inverse is linear. So F is linear, and F inverse is linear. Now, F is linear tells me that F itself is given by a matrix. So F is linear means there is a matrix such that F of X is A times X for any vector X. And therefore, since F inverse is linear, there has to be a matrix such that F inverse of X is given by B times X for some matrices A and B. And these matrices, remember that the F and the F inverse go from Rn to Rn. So these matrices are n by n. So given one of them, given the matrix for F, what is the matrix for B? So here, the question I want to answer now is, what is the matrix for F inverse given F and the matrix for A? Well, the property we're looking for is that, well, what we know about the inverse is that F composed with the inverse is the identity map from Rn to Rn. And also F inverse composed with F is the identity. Those are the basic properties of the inverse function. But that tells me something about the product of A and B, because I know that the matrix of a product of a composition of linear maps is the product of the matrices. So we have, so this tells me on one hand that the composition of A times B, that has to be the matrix of the identity map, which is the identity matrix, the n by n identity matrix. And this tells me that if I compose F inverse and F, so if I multiply B times A, which would be the matrix of this transformation, that also has to be the identity, the n by n identity. So I'm looking for a matrix B, so I want to find B such that A times B is equal to the identity and is equal to B times A. So how do I find that matrix B, which we're going to call the inverse of A? More generally, I want to know, given an n by n matrix A, I want to know if is there an inverse matrix such that A times A inverse is the identity and A inverse times A is also the identity. So under what conditions there will be an inverse matrix, and if so, how do I find such inverse? let me give you some examples of inverse matrices. So let A be 3, 7, 2, 5. Then there is an inverse. I'm not telling you exactly yet how I found it, but the inverse matrix, it turns out it's going to be 5 minus 7 minus 2, 3. And I can verify that it is an inverse. It satisfies what I want. If I multiply 3, 7, 2, 5 times 5 minus 7 minus 2, 3, what do I get? Remember, I multiply this vector by this vector. So that is 3 times 5, 15, minus 14, I get 1. 3 times minus 7 is minus 21, plus 21, I get 0. 2 times 5 is 10, minus 10 is 0, and 2 times minus 7 is minus 14, plus 15 is 1. I do get the identity, and you can check yourselves that if you multiply in the other order, 5 minus 7 minus 2, 3 times 3 is 7, 2, 5, I get the identity once again. So how do I find these inverse matrices? Let me show you how we are going to find it. So if I start from, let me give you an example. I'm going to try to find the inverse matrix for 1, 0, 1, 1. The inverse matrix will be some other square matrix, A, B, C, D, such that when I multiply them together, I get the identity matrix, right? So this looks like, if I multiply this, this is actually, remember, by the definition, the very definition of multiplication of matrices, this is this, that's the first column, and 1, 0, 1, 1 times BD is the second column, is equal to 1, 0, 0, 1. So there is two linear systems that I'm trying to solve at the same time. I'm trying to solve 1, 0, 1, 1, AC is equal to 1, 0, and I'm trying to solve at the same time this times BD is equal to 0, 1. If you put it in augmented form, it is this system, and this system is this system. But you see, if I'm trying to, I'm going to have to row reduce both systems, but since the left-hand side is the same, as I try to row reduce, the work on the actual matrix is going to be the same, and then the work on these augmented columns is going to be a little bit different. So what we do is we actually solve both systems at the same time by row reducing the super augmented matrix with two augmented columns. So if I row reduce this one, it will keep track of the solutions for this and the solution for that, and it will give me actually the solutions to everything, to A, B, C, and D, all at the same time. So let's row reduce that one. If I row reduce this one, let me keep the first row and then subtract from the second row the first row. I get 0, 1, minus 1, 1, and you see that I'm done. I've row reduced. So the answer is going to be that the inverse is whatever is in here. It turns out that the inverse is going to be precisely the matrix 1, 0, minus 1, 1. And now we can actually check what happens 1, 0, 1, 1 times 1, 0, minus 1, 1. I get 1, 0 times 1 minus 1, that is 1. 1, 0 times 0, 1, that gives me 0. 1, 1, 0. 1, 1 times this gives me 1. And if I go the other way, it looks like we had only tried to solve this in this order. But if I multiply in the other order, what do I get? I get 1, 0 by 1, 1, that's 1. 1, 0 by 0, 1, that's 0. Minus 1, 1 by 1, 1, that's 0. And minus 1, 1 by this is 1. So it works. This is the inverse matrix. So you can do that for any general matrix, for at least for any 2 by 2 matrix, we can do that process and show that if I have a matrix A, B, C, D, if I do the row reduction of, just do the row reduction of A, B, C, D, and 1, 0, 0, 1, and see what you get, what you can prove is that the following, and put D to be A, D minus B, C, then 1, if D is non-zero, then actually what happens is that in the row reduction, what I get is that the inverse matrix is given by 1 over AD minus BC, which is that capital D, times the matrix D minus B minus C A. While if D is 0, then A is not invertible. So there is no inverse. There is no inverse matrix A. So for example, let me show you one first quick example. We had previously the matrix 3, 7, 2, 5. So let's do that. Let's start with the matrix 3, 7, 2, 5. For this matrix, D is 3 times 5 minus 7 times 2, so it's 15 minus 14 is 1. So yes, there is an inverse, and the matrix that is the inverse has to be 1 over 1, so just 1, times, and then we switch the elements in the diagonal, 5, 3, and then we change the sign of the elements of the main diagonal. So the inverse matrix should be 5 minus 7 minus 2, 3. And you can check that that will be correct, and that is the inverse. For example, let me give you another example. What if A is the matrix 1, 2, 3, 4? Then here D is 4 minus 6 is minus 2. So that is non-zero. So there is an inverse matrix, and here the inverse will be 1 over minus 2 times 4 minus 2 minus 3, 1, which is the matrix minus 2, 1, 3 halves minus 1 half. And that is the inverse matrix. And just as an exercise, why don't you check yourself that A times A inverse is the identity, and also that A inverse times A is the identity in this case. Now, I want to talk about an application of this, of inverse matrices to solving linear systems. So suppose I have to solve the following system. X plus 2y is equal to 5, and 3x plus 4y is equal to 6. This, in matrix form, is the system 1, 2, 3, 4 times xy is equal to 5, 6. Or, if this is the matrix A, this says that A times xy is equal to 5, 6. Now I have an inverse matrix, so I can multiply these equation by the inverse matrix on both sides. On the left, that will be the same as multiplying with the inverse matrix the vector 5, 6. And on the other hand, this is on over here, this is the identity matrix times xy, which is just xy. And what this tells me is that the solution is given by the inverse matrix times 5, 6. So let's check that. So this is telling me that I can actually simply find the solution by multiplying the inverse matrix times the vector 5, 6. I had calculated the inverse matrix was minus 2, 1, 3/2 minus 1/2. And if I multiply by 6, I get minus 10 plus 6 is minus 4. And 3/2 times 5 minus 6/2, that is 9/2. So apparently the solution is minus 4, 9/2. Is that true? Let's check that it actually solves our system. So minus 4 plus 2 times 9/2 is 5, and 3 times minus 4 plus 4 times 9/2 is 6. So yes, this is a solution of my system. So that is a solution. And in fact, because of what I did, the existence of the inverse matrix is going to tell me that this is in fact the unique solution of the system. That is in fact a theorem that if A is invertible, an invertible n by n matrix, then the system AX is equal to B has a unique solution, which is X is equal to the inverse matrix times B for any B. And this works for any B in Rn. That is precisely the solution. So this is great because we can solve systems by computing an inverse matrix. Now, some properties of the inverse matrix that are very useful are the following. First of all, what is the inverse matrix of the inverse? That is itself. That means what matrix would I have to multiply A inverse to get the identity? And that would be A, so that makes sense. The inverse matrix of a product, it turns out, is the product of the inverse matrices, but be careful because it is in the opposite order. So the inverse matrix of A times B is B inverse times A inverse. Let me actually show you that that is true. Let's multiply AB times B inverse A inverse. Matrix multiplication is associative, so I can multiply first B times B inverse and then multiply by A inverse. Now B times B inverse is the identity, so this is A times identity times A inverse. A times identity is A, and A times A inverse is the identity. So you see that this matrix is the inverse of that matrix and vice versa. And finally, the transpose inverse, so this is for an n by n matrix, so A and B are n by n invertible matrices here. Then the inverse of the transpose is the transpose of the inverse. So here, this T, remember that means transpose, the transpose matrix. Great. Now, I want to still try to figure out, given a matrix E, whether it's invertible or not. So how do we do that? Question, given A, an n by n matrix A, is A invertible? We know the answer for a 2 by 2, and the way I found the answer for the 2 by 2 by doing a row reduction of the matrix with, remember we did it by row reducing A, B, C, D with the identity matrix on the right hand side. That is the method that works for all matrices. For all n by n matrices, I can do the same. So an n by n matrix A is invertible if and only if it is row equivalent to the identity, to the n by n identity matrix. And in this case, any sequence of row operations that reduces A to the identity also transforms at the same time the identity to the inverse matrix. So what I mean is precisely this, that first of all, if this matrix row reduces to the identity, then it is invertible. And if I row reduce this one to the identity and keep track of what's happening to the identity matrix on the right-hand side, what ends up on this side after all those transformations is the inverse of the matrix. So let me show you an example of how this works. Let's just start with the matrix, for example, just in a 2 by 2 case, and then we'll do some 3 by 3 case. So is this matrix invertible? Well, then if so, we're going to find the inverse, and we do that both at the same time. We are just going to row reduce the matrix and see if by row reducing the matrix with the identity matrix on the right hand side, if I'm able to row reduce to the identity, the inverse will appear here. And if I can't reduce it, then it is not invertible. So I can row reduce this by creating a pivot of 1 at the top that I have to divide by 3. And then what I'm going to do is eliminate these 4. That elimination brings me to 1, 2/3, a third, 0, 0, a third, minus 4 over 3, 1, and then eliminate the rest. So I'm going to make this a 1 and then subtract from here. So it ends up being that it is reduced to the identity, and on the right hand side I get this matrix, and therefore, yes, it is invertible, and the inverse is precisely the matrix that appears on the right-hand side of the augmented line. So this is the inverse matrix. And you can check that A times A inverse is the identity, and that A inverse times A is the identity to make sure that's right. Let's do an example of a 3 by 3 matrix. So I'm going to do the same operation, but this time on the matrix. The matrix A is going to be 1, 0, 2, 0, 1, 3, minus 2, 0, 1. And then we start with 1, 0, 2, 0, 1, 3, minus 2, 0, 1. And in the augmented columns, I'm going to super augment it with the identity matrix. This is row equivalent to, I already have a pivot of 1 there, so I'm going to leave it alone. Then I'm going to leave the second row actually just the same and reduce the third row by adding twice the first row. Then I get 0, 0, 5, 2, 0, 1. And then once again, now divide by 5 in the last row. 1, 2, 0, 2, 1, 0, 0, 0, 1, 3, 0, 1, 0, 0, 0, 1, 2 over 5, 0, 1 over 5. And then just keep going and row reduce all the way to the identity. I get 1, 0, 0, 0, 1, 0, 0, 0, 0. So it does, whoops. No, there is a pivot there. This is a 1. So it does row reduce to the identity. And here I get 1 over 5, 0, minus 2 over 5, minus 6 over 5, 1, minus 3 over 5, 2 over 5, 0, and 1 over 5. So yes, it is invertible. It is invertible. And the inverse matrix is that matrix, 1 over 5, 0, minus 2 over 5, minus 6 over 5, 1, minus 3 over 5, 2 over 5, 0, 1 over 5. And you can check that this works. So please do check that if I multiply the matrix A and A inverse, for example, I do get the identity. I can check that, for example, 102 times this one will be, um, so it is 1/5 plus 2 times 2, 4/5. So 1/5 plus 4/5 is 1. So that it will be the first coordinate of the identity matrix. That gives me a 1. So you can double check that work to see that it solves that. That is the inverse matrix. Finally, let me just give you an example of how to use that inverse matrix to solve a system. So suppose I want to find a solution to x plus 2z equals 1, y plus 3z is 2, minus 2x plus z is equal to 3. If I put this in matrix form, this is given by the matrix we just worked with, equals 1, 2, 3. So this is a system AX equals 1, 2, 3. And if I multiply both sides by the inverse matrix, that's going to be, on one hand, this is the identity times x, so this is just the vector x. And on the right-hand side is the inverse matrix times the vector 1, 2, 3. So to find the solution, I just have to multiply my inverse matrix, which we just found out, we just computed, to be this matrix. I have to multiply by 1, 2, 3, by the vector 1, 2, 3. And what I get is 1 minus 6/5, that's minus 5/5, so it is minus 1. And then if you do this computation, I get minus 1, minus 1, 1. So it turns out that this is the unique solution of the system. And you can check that it indeed solved this system. Minus 1 plus 2 is 1, minus 1 plus 3 is 2, and 2 plus 1 is 3. So this is a solution to the system. And because there is an inverse matrix, it is the unique solution to our system.